And welcome muli sa lahat. Welcome to our second topic of food physics. Obvious naman po dun sa 4 picks 1 word in the title of this video kung ano yung mga words doon sa naunang 2 slides. So today, we'll be discussing mass and density. So last time, we've looked at the basis for all of our measurement of physical phenomena, which are the base SI units, and how they were developed, and even the recent developments worldwide regarding changes in the long-held definitions of some of these base SI units, which will somehow affect how we measure our physical properties of food. So let's start with probably the most common, mass and density. Right, so ever since you were young, the moment you were born, you have been put on a sort of weighing scale, and we probably encountered density from, let's say, elementary school, when you had those experiments where one liquid was put on top of the other, and um, the liquids would stratify into layers, or perhaps when you um, tried playing in the water and saw that some items floated while others sank. No? So those are all related with mass and density. Of course, unang tanong, ano nga bang significance ito sa pagkain? Well, malaking malaki. Kasi bibili ka ng kahit ano, it's usually sold more often than not by weight, or if not naman by volume. And what relates weight and volume? Aba, density. Okay, so let's start. So mass is defined as the heaviness of the body with its SI unit in kilograms. Probably nung bata kayo ay madalas na nagpa-pop up yung question, ano ba ang mas mabigat? Isang kilong bulak at isang kilong pako. Obviously, by the measure of, by the definition of mass, neither should be heavier. So hindi ko alam kung etong si ambitious poster, kung anong ambisyon niya sa buhay, at bakit ganyan siya mag-isip, but this just goes to show, without a proper knowledge of the definition of mass, you're bound to have a mistaken idea about what mass or bigat is. So allow me to read this to you, from Brian Resnick, an NIST scientist. How do you know what something weighs? I know there's an obvious answer. You put it on a scale. But when you go to a grocery store and weigh a bundle of apples, how does that scale know what a pound of fruit feels like? For mass measurements to make sense, we need a fixed point of comparison. Those apples need to weigh more or less than something. To avoid chaos and to allow our economy to function, that something has to be universally recognized. The scale at your grocery store was calibrated with a weight that was calibrated with a weight that was calibrated with a weight, and so on. And all those calibration traces back right here in the bowels of NIST. Consistent weights and measures matter for more than groceries. Imagine if Boeing couldn't figure out precisely what an airplane weighs, or if the pharmaceutical industry couldn't determine the exact mass of a tiny, potentially lethal dose of medicine. Alright, so of course by now we've seen na nagbago na yung definition ng kilogram, but nonetheless, it is based on something. And again, lahat ng experiments natin at lahat ng binibili nating nakatimbang ay nakabase doon sa, well, hindi na siya yung prototype kilogram, but rather the the balance that could accurately measure that weight, na hindi nagpo-propagate yung error masyado, no? So the definition of a kilogram started with simply being 1 cubic decimeter, or 1 liter of water at the temperature of its maximum density, which is around 4 degrees Celsius. In 1799, it was changed into a piece of platinum that's perhaps made to weigh the same as the 1 decimeter of water. 1889, it was the international prototype kilogram. Okay, and approximately 50 micrograms yung nawala dito in a span of almost 130 years. So that picture over here, yan po yun. Nakalagay siya sa ilang layers of glass na under vacuum stored in a vault, and only periodically put out to be checked na yung timbang. Pero ironic kasi yung pinapang-timbang sa kanya nakabase din sa kanya bilang calibration weight. So I'm not sure how they knew that it lost 50 micrograms in 129 years. So currently the definition of the kilogram again is um, the fixed numerical value of the Planck constant H when expressed in unit joules, which is equal to kilogram meter squared per second. However, the meter and second as base SI units for length and time respectively are also defined in terms of the constants C and delta V CS. So what's happening now is we're defining a constant with other constants, okay? And just to say, it's no longer a physical object that is the basis for our kilogram, and therefore technically dahil constant nga yung pinagbasihan mo, hindi na magbabago yung 1 kilogram. You just need to have a piece of equipment that can, based on this constant, measure the actual kilogram. And for that, we have what we call the Kibble balance, which is yung pinaka-equipment na kayang mag-measure ng kilogram based doon sa Planck constant. Of course, it was named after the person who invented it, and it works by offsetting the weight of the test material by a force produced when electric current runs through a coil wire, okay, immersed in a surrounding magnetic field. Okay, so worldwide, ito na ngayon, imbis na prototype kilogram na pinapang-calibrate ng ibang weights, ang ginagawa na lang is kinakalibrate sa Kibble balance yung weight, and then yung weight na yan yung ginagamit na pang-calibrate naman ng ibang mga weight, okay, or balances. So there's actually some people who tried to make a Kibble balance out of Lego blocks. You can watch it in the next video. Next slide. By now, we're probably all too familiar with the difference between mass and weight, where mass is constant and weight is dependent on the acceleration due to gravity and is measured in newtons, while mass is in kilograms. In actuality, the world is not perfectly round, and differences in elevation aside, so we actually have different values of g, or the gravitational constant, which isn't really so constant around the world. We usually use the 9.81, but in different parts of the world, here you can see 9.806 sa Switzerland, sa Colombia 9.77, and sa Iceland 9.82. What this means is if you were to take the same balance and use the same weight for calibrating it, depending on where you are in the world, it would display a different value. So you would need to have some sort of offset mechanism for advanced balances to calibrate it properly, no? Kasi ang laki ng diferensya naman, kumusta? Ilang grams na yan, no? Okay lang yan kung malugi ka ng 4 grams or so dun sa prutas or gulay mo. Pero kung dose ng medicine yan, then you really have to take that into account. So that's physics for you, no? So now we discuss ano bang difference ng scales tsaka balances. So we often hear them and think we use them interchangeably. Why do we have an analytical balance in the lab and a weighing scale at home? So when we say scale, it usually uses the force of gravity through the deflection of spring or strain gauges which measure force, so to display weight. So talagang weight yung dinidisplay niya kasi something with the same mass under a different gravitational field would reflect different weight. On the other hand, a balance compares the mass of two objects, so such as this one. So in which case, hindi magbabago yung pinaka-reading ng balance regardless of the gravitational pull. Kasi nga, um, kino-compare mo siya sa isang object na kung magbago man yung timbang ng object na yun dahil sa gravity, it's still being compared relative to that object. So if the thing you're weighing weighs the same as the object being compared to, regardless of the gravitational field, horizontal yung position nila sa balance. Okay? So you might wonder right now, so ano pala yung analytical balance? What does it compare yung pinapatong mo doon to? Kung parang wala ka naman nakikitang um, piece of weight na kumokontra dun sa weight na pinatong mo sa analytical balance mo. Okay, I'll leave you hanging dun sa question ko and babalikan natin yan mamaya. But let's start by defining terms, okay? So when you say capacity, it is the largest weight a balance is capable of weighing. You do not want to exceed this capacity as of course, mostly if it's an electronic balance, it will already display an error. And while it's not likely to immediately damage the sensor if it's just slightly above, you'd still want to consider no, kung halimbawa tingin mo mas mabigat or near capacity na yung i-weigh mo, try mo muna siyang timbangin sa mas larger capacity na balance. Readability is the smallest increment displayed by a scale. So for example, sa usual analytical balance natin sa lab, is 1 milligram or 0.0001 gram. Typically, the more decimals there are sa readability, mas mahal yung balance natin. So an analytical balance usually costs somewhere near 100,000 pesos, more or less. Linearity, on the other hand, is the quality of delivering identical sensitivity throughout the weighing capacity of a balance or scale. One way to test this is by weighing two objects separately, each of which is approximately around half of the capacity. And then you weigh these together and yung weight nila separately when added should equal the weight kapag parehas silang nasa balance. No? So that is to say, at halfway through the scale, does it measure the same proportional mass as the as both of the objects combined? Okay. Minimum weight, on the other hand, is the standard deviation of repeatability divided by the required accuracy. So as it states, no, hindi porket 0.0001 yung readability ng balance mo, ay 0.0001 na rin yung pwede mong itimbang doon. So usually balances calculate, the manufacturers calculate this for you, as you'll see in the next slide, and state that a balance has a certain minimum weight such that kapag below doon yung gagamitin mo, well, meron ka ng error sa weighing. Although this is usually required for pharmaceutical applications, depende kung gaano ka-critical yung timbang dun sa ginagawa mong research, ay you might want to follow this as well and not use a balance to weigh anything before the minimum weight. So if you're gonna have something in the lab, you might as well ask the lab technician for the manual para alam ninyo kung hanggang gaano kababa yung reasonably pwedeng timbangin doon sa balance kahit na kaya pa niyang i-display yung weights lower than that. Lastly, you have precision or readability, which is the amount of agreement between repeated measurements of the same quantity. So, if halimbawa nagpatong ka ng barya doon 10 times, then dapat iisa lang ideally yung kanyang display na value every time, or there's just a very small difference between the among the 10 readings. No? So dito makikita natin yung example ng brochure ng isang analytical balance. You can see here that you are not supposed to use this for anything weighing more than 220 grams. Its repeatability and readability are the same at 0.1 milligrams. However, if you're gonna use it for pharmaceutical, especially, you don't want to use it for anything lower than 82 milligrams, even if it could read zero point 0.1. Okay. So, and then of course, there are a variety of applications that it's generally used for. And for our purposes, of course, gumagamit din tayo niyan sa food science. So as you can see, hindi mura ang analytical balance. This is what, around 80,000 plus pesos. And dahil hindi pa masyadong gina-adapt ang SI sa ilang mga bansa sa mundo, so we actually have here different weights. No? Typically, of course, we use grams. Pero may US uses pounds and ounces and whatnot. Scientists use newtons, and then carats, I think, is still used for jewelry. Okay, so yan. Also, we also have the average response time for a balance. No? Kasi kung marami kang tinitimbang, ayaw mong mag-antay ng matagal para lang mag-equilibrate yung balance mo kasi that's time lost. No? Especially if you're weighing things in succession and things that, let's say, out of the oven, out of the desiccator, you have something you need to weigh and it absorbs moisture the longer you put it out in the weighing pan. No? So you'd want something with a fast response time of, well, maybe less than 5 seconds. So I am not sure if you were able to encounter something like this in your maybe high school. Kami nagamit pa namin to sa FS106 noon. It's not digital, but it's pretty good for certain uses. No? At kahit brownout, magagamit mo siya. So how do balances work? Again, when you have a balance, you ideally, you have the weighing pan and the counter weight or yung weight na pang compare. So how this one works is you move these slider weights. No? Parang yung timbangan lang madalas nakita nyo sa ospital na may parang height measurement din. So it's just a smaller version of that. And then as you can see, yung parang pinaka fulcrum niya ng seesaw is over here. Okay. So you slide the weight bars and kapag balance na doon sa equivalent weight dito, yung pinatong mo, ay yung arrow nito nandun sa middle, di ba? Parang may diamond dyan, and sa middle yan tuturo. Okay. Then of course you can use these calibration weights, or rather extra weight, sorry. Yan, isasabit nyo dito sa dulo. Mas mabigat yung kailangan ninyo. So, how do electronic balances work? There are different types. Although I don't know if the load cell type can be considered a balance kasi it acts more like a scale, no, in a sense. But for the load cell type, you have a load cell, no, parang ganyan yung itsura nila. It's a strain gauge, so it measures forces applied to it para magbe-bend siya. And you measure that bending or deflection. Okay. So, pag may pinatong ka sample, the elastic body flexes in response to that sample. So it may expand or contract. And then the electric signal depends on how much that expansion or contraction is, and it's translated into an equivalent weight. For electromagnetic types like the cable balance, instead of having a weight on the other end, you simply apply electromagnetic force. Okay. And you measure the amount of current generated, and that would have an equivalent translation in weight. No? So parang yung sa cable balance lang na concept. What are the advantages and disadvantages of these two types? So the electromagnetic type has higher accuracy. Of course, the cable balance is the standard for that. Compared to the load cell type, which is, even though not as accurate, is simpler and easier to produce, and thus the disadvantage of the electromagnetic type is with respect to its complexity, and you cannot use it for yung gawa ng maliit na electromagnetic type balance. Hindi madali. On the other hand, the load cell type has a limited accuracy. And in terms of precision, of course, yung electromagnetic type, gagamitin mo lang siya sa mga precision applications such as analytical, while the load cell type can use it for sa mga hindi naman masyadong kailangan ng accuracy. No? For example, yung mga supermarket scales, you don't need analytical level kasi yung plus minus few grams, afford mo naman na either ikaw yung malugi or malugi yung consumer ng kaunti. You don't need it to the milligram levels if you're buying kilos of meat and say, hey, it's off by 50 milligrams, give me my 20 centavos back or 10 centavos back. Ganon, di ba? So, noong unang panahon, yung prototype kilogram was used to calibrate a higher level reference weights, which are used to calibrate lower level reference weights, and which are used to calibrate again lower level reference weights. You get the point, no? And usually, kapag tinrace mo, the lower levels of reference weights would trace up to higher levels and then ultimately to the prototype kilogram. However, with the changes in 2019, so even though wala na tayong prototype kilogram, yung sistema ng paggamit ng calibrated reference weights typically is still in effect, no? So we have a calibrated mass standard. They differ in class level depending on how close they are, at least back then, to the prototype kilogram. Okay. So you place that mass standard on your balance or scale, and the deformation is read as either an angle, distance, or electronic voltage, depending on ano yung mechanism ng balance or scale mo. And you expect the mass to read out something like, if it's a 100 gram standard, dapat 100 grams yung basa niya, with a certain plus minus, of course. So you construct a calibration curve by looking at ano yung timbang ng mga different masses na nilagay ko versus ano yung nabasa ng scale sa kanila. Okay. Typically, you have internal and external calibration. So for example, sa laboratory natin, most analytical balances would have a self-calibration procedure, but you can also use an external, so yun yung internal, no? You can also have ikaw yung magka-calibrate na maglalagay ka ng calibration weights dun sa analytical balance. Although you can also, usually periodically ang ginagawa is meron ka ring tinatawagang outsiders na accredited calibrators to usually periodically check the calibration of your balance on top of the balance's own calibration system, and you as the end user calibrating it using your own lab calibration weights. Okay, so yung external calibration by accredited service providers, typically parang once a year. Now, when I was in the industry, we externally calibrate annually, not just our balances, but also things like our thermometers, to make sure that they are still professionally maintained. Okay. So, ang tawag pala sa mga institutions na nagde-deal with calibration is metrology institutions, no? So we have a local metrology institution under ng may division ng DOST on metrology, and we also have NGO sa Philippines on metrology. So tulad nga ng sinabi ko, there are different weight classes for calibration weights, no? So for the American Society for Testing of Materials, you have classes 1 to 4. Class 1 is, of course, the highest tier for the best precision work up to 0.01 milligrams, and Class 4 would be those for student use. So, generally, pag mas maraming decimal, mas mataas yung class, and kung mas critical yung application. No? Kasi syempre, iba naman yung pang-lab experiment mo lang, iba lang yung funded research project siya na doon nakahinge yung, let's say, medical discovery mo or something. Similarly, the National Institute for Science and Technology of the US, NIST, has weight classes. Okay? So, ito naman by letters yung classes nila. So you can just look this up, no? But generally, we want the appropriate calibration weight class for our purposes. So iba yung pag student lab lang, iba din of course pag funded scientific inquiry or research yung ginagawa mo. Iba din syempre yung pang supermarket lang dahil hindi mo naman kailangan ng milligram sa supermarket scales. But what's important is that all scales must be calibrated as appropriate for its use. So the International Organization for Legal Metrology, OIML, hindi kasi English yung original ano niya, no? Kaya ganyan yung arrangement ng letters. Also has weight classes from E1, which is the primary reference standard, to the lower classes. So I own a set of M3 weights. So medyo mumurahin lang siya of course kumpara sa mga yan. And okay naman siya for its general purpose, no? But again, you could use either, depende no kung meron lang kayong sinusunod na regulation, pero yung OIML, NIST, or ano, ASTM, you could use either of them kung wala namang restriction sa ano yung dapat yung sundin for your particular purpose, no? So it's fair to say that weighing as a concept has been invented even before we were able to adequately explain no, yung the force of gravity and all that, and as such, most methods of weighing is practically a comparison of an unknown weight and a standard weight. No? So you are comparing the ratio of downward forces, in this case of the unknown, and the quote-unquote weight force of the mass standard, which depends on the assumption that the gravity is the same in your location for isa lang naman talaga, no? For any given location, and that you are determining the ratio of the weight forces of the two. Of course, one disadvantage of this is that when you're weighing something in atmospheric conditions, you have atmospheric air surrounding you, and that atmospheric air provides a sort of error dun sa natitimbang mo, at lalong hindi ka makakapagtimbang ng isang bagay na mas magaan sa tubig. So imagine weighing something underwater. If you have a weighing scale underwater and you put something on top of it, definitely the buoyant forces of the water acting upon it can cause some sort of error in the reading. And at the same time, you cannot weigh anything lighter than water because it will float. So that we have to correct for atmospheric buoyancy. Okay. So, kasi essentially, ang implication noon is, if you were to weigh something in vacuum, it would be different because compared to atmospheric air. Kasi nga may atmospheric buoyancy ka. Again, two things, implications nga is, anything lighter than air cannot be weighed with a scale relying on downward forces, and at the same time, what we measure is slightly smaller or mas magaan, quote-unquote, than when we measure these things in vacuum. Next is, the measured weight is dependent on the density of air in a specific location, kasi as we know, hindi rin naman uniform yung density of air. Mas manipis ang hangin the higher your elevation is, and so on. And lastly, substance with a much lower density or a density much closer to the density of air will have a higher error or greater difference in its weight versus the weight in vacuum. So, hindi naman ito masyadong malaking problema kung ang tinitimbang mo ay bakal, mabibigat na solids, tubig, or what. Pero kung nagtitimbang ka ng very mas less dense pa than water na mga bagay, okay, then you have to take into account yung atmospheric buoyancy. So even though this affects food materials as well, the weight difference isn't actually super big, no? So kung nagtitimbang ka lang, let's say, for your baking or for your batch process, medyo maliit lang naman yung effect nito, okay? But as you can see, the less dense a substance is, okay, the more yung difference ng actual weight niya in vacuum versus the actual weight in vacuum versus the weight obtained or displayed by the balance. Okay, so from that you can experimentally derive correction factors for it, no? So as you can see here, yun yung effect ng buoyancy, let's say on a spring scale, because if you're not in vacuum, the air is somewhat pushing it up para mas mababa yung deflection ng spring ever so slightly. Very important yung calibration natin, no? For our results. And what are the things that could affect our calibration? Definitely, if hindi regular yung calibration mo or balahura yung pag-calibrate mo ng balance, ay magkakamali yung actual weight. Okay, posible rin na faulty yung electronics or mechanicals ng balance. So, unang red flag niyan is, well, usually pag nagka-calibrate tayo, may logbook yan. So, although internally, every time you turn on a modern analytical balance, it does some sort of self-check and could even display error messages. Kung ikaw halimbawa as a student or yung lab technician, every day, papatungan mo yun ng the same calibration weights and you list down kung ano yung nabasa niya at different points on the balance, no? Kasi square yung patungan or bilog, top, bottom, left, right, middle, and then does it read differently. So you can periodically review yung logbook mo kung may drift ba na nagaganap dun sa timbang or something. Tapos pwede mo i-contact si manufacturer and usually, yun nga, gusto mo na parang annually bisitahin ka ng manufacturer for their own check-up and calibration of your balance. Also, calibration weights could be erroneous, no? So over time, pag nabagsak siya, natatapyasan yung bakal, or na kinakalawang siya, or kung usually these weights are handled with tongs because fingerprints and other contaminants might make the calibration off dahil nagsisettle yung dust doon or what, or moisture. Okay, and then pagdating naman sa method mo, you could also encounter air turbulence. Kaya nga yung mga analytical balances especially, meron silang sariling glass cabinet, no? Kasi kung mapapansin nyo kung sa lab, nakatutok yung electric fan habang nag-weigh ka ng sa analytical balance, hindi nag-stabilize yung reading ng balance mo kasi yung effect ng air, may downward force siya, nare-read yung balance mo kasi ganun siya ka-sensitive. And of course, if for example, different people do the calibrations every day, if they don't follow the exact same method, then baka iba yung result na makuha nila dun sa calibration.